Before I continue on with what we were covering last class, let's just do a quick review of when we started the lesson. So we had began uniform motion, and we started with this question here, and it asks us to draw a velocity time graph showing a 0.1 meters per second squared uniform acceleration over a 5-second period, and the object is going to be starting at rest. So first we identify our uniform motion, our uniform accelerations, 0.1 meters per second squared. So for every second that goes by, the object will be increasing its speed by 0.1 meters per second. So at the very beginning, we're told it starts at rest, so the speed will be 0. Then after 1 second, the speed is going to increase by 0.1 meters per second. Then it will increase by another 0.1 meters per second, bring us up to 0.2. Again, increases by 0.1. We're up to 0.3. Then we'll go to 0.4 and 0.5 meters per second at the end of the time. We then have to plot a graph of this. So on our velocity time graph, we put in each of our matching points. And by looking at this, we know we're going to get a straight line with a constant slope. So slope has stayed the same throughout the motion of the entire graph. We're asked to calculate the slope of this graph, so the rise over the run, and the rise here. So we went from 0 meters at rest, ending at 0.5 meters. Per second. And this happened over a 5-second period. So that's our run. From here to there. So slope 0.5 meters per second divided by 5 seconds, and it works out to 0.1 meters per second squared. So what does the slope represent? Well, the slope of a velocity time graph will always give you the acceleration of the object. And remember, this is just for a VT graph. To our next slide. We had talked about this one in class. And then here, second question. Draw a distance time graph now. So not a velocity time graph, but instead we're asked for a distance time graph. And it's another object with a uniform acceleration of 4.0 meters per second squared. And that's happening over a 5-second period, and it starts in rest at a position of 0 meters. Now, we've had some discussion whether these numbers are right. They are, and there's a formula that we'll go over later on how to calculate the distance traveled when you have a uniform acceleration. So starting from rest, at the very beginning, you would have traveled 0 meters. And then every second that goes by, you'll be traveling 4 meters per second squared faster. I think the confusion that came in during class was that people were thinking that you would be traveling at this point at 1 second. By that time, you travel at 4 meters per second. And that's not necessarily at the end of 1 second you'll be reaching this speed. But what you have to remember is that the speed of the object is starting at 0 meters per second, and it's building up to 4 meters per second by the time you get to 1 second. So it hasn't been traveling 4 meters per second for 1 second. It's only at the end of that time do you reach it. So you wouldn't have traveled 4 meters as we were discussing in class. you would have if you were traveling for the whole time at 40 meters per second. But what you have to remember is that the speed started at 0 and is increasing up to 4 meters per second. So each of these distances traveled here are correct. So if we plot these on a distance time graph, so in 1 second you travel 2 meters, in 2 seconds 8, 3 seconds 18, 4 seconds up to 32. So again, 32 will be here if we're reading our scale right. So I'll just, in case people are not seeing where the points are coming from. So 4 seconds, you would have reached 32 meters. And at 5 seconds, up to 50. Now, trying to draw a straight line here, you wouldn't get one in there. It won't work because you don't have a constant velocity. What we have is actually an exponential curve. So the speed is increasing exponentially. It's not increasing at a constant rate. And if you think about it this way, the distance that you cover here in 1 second, in 1 second here, you've only covered 2 meters. But in another second, you've covered 6 meters. So the amount of distance you're covering keeps increasing. And you can see that here. Here, you've covered 2 meters. Then from 2 meters to 8, well, you've added on an additional 6 meters. Then from 2 seconds to 3, you covered an extra 10 meters. Then from 3 seconds to 4, we covered an additional 14 meters. And from 4 seconds to 5, an extra 18 meters. And you'd see that here by looking at the change in height between each of these points. So for every second that goes by, you don't have a uniform distance that you're covering. So first just in 1 second is 2, then your distance you're adding on an extra 6 meters, an extra 10 meters, 14, 18, which gives you the shape of this graph. Okay, so some points now you need to pay attention to. So first recall that slope of a distance time graph equals speed. The problem we come up with now is that how do we find the slope of a curved line? So when we look at what we have here, we have a distance time graph. How do we find the speed of this object? Because the slope is constantly changing, so you can't get one speed at this point. So we had an object that traveled like this. So after each second, it will cover 10 meters. Another second, you cover an additional 10. It's got a constant slope. So speed in this case, 10 meters in 1 second, be 10 meters per second. And that will be the same as if you went up here. And you say, well, I would have covered 20 meters in 2 seconds. Again, constant speed, 10 meters per second. And that's when you have a straight line. But the problem is, what happens when you come up with a curved line? We can't apply the same techniques here to do that, because the slope of the line is constantly changing. The line has a fairly low or flat slope at its beginning, and it gets steeper as time goes on. So if you look at the slope of this portion of the line, so if you look at the slope here and try and compare it to another section of the graph, say here in another 1 second interval, the slope at this part is much steeper than the slope here. Now that would tell you that speed's increasing here, and it's much higher than speed back here at the beginning. So where's the speed of the object the slowest? And where's the highest? Well, speed is the slowest here, at the flattest section. So at the beginning. Or when there's the smallest slope. And when you think about slope, think about skiing. Where would you have the fastest speed? Here at the bottom part of the hill, or here at the top? So if someone were going skiing, so as you're coming down here, you have the steepest slope, and this is your fastest speed. So here at the end of the graph. And what's the relationship between slope and speed? Well, I've already said that. So the steeper the slope, or the higher the slope, or bigger the value, faster the speed. Now, so your problem that you need to know how to figure out is how do you find slope? So determining object speed from a distance time graph, the method that we're going to use is called tangent method. So here. And the slope at any particular time on a distance time graph equals the instantaneous speed at that time. Now, before we go any further, instantaneous speed. Let's go back one. Here. So if you find the slope at this very point, right here, you'd have the speed at that very moment in time. So think as you're skiing down a hill, and I calculate your speed at this very instant. Well, your speed here will be different than your speed there. So when you find the speed at one particular moment in time, at a very instant, it's called instantaneous speed. So think of the drag car clip we played in class earlier the week. The speed of a drag car at the very beginning is going to be much slower than the speed at the end of the race. So if we went back here, we'd watch that clip there. So as that car, just as it starts, its speed at that very instant is not going to be the same as if you looked at it half a second later or any other point after.